Out of a sample of n is equal to 625 students interviewed, 139 had missed at least one class last week. Let p be equal to the proportion of students that missed at least one class last week. Conduct a test with the intent of establishing that the proportion of students that missed at least one class last week is greater than 0.20. Test at a level of significance alpha is equal to 0.05. Okay, so first let's put down the parts that we're going to need. So n is equal to 625. Okay, and we have to notice that this is going to be binomial distribution because we're talking about the counting number, the number of students, and we're going to be approximating it using the normal because that's what you're going to have to do when you're testing for a hypothesis, null hypothesis, right? So to make sure that we can do that, we first test the NP value. Okay, now to test NP value, we have to find the NP hat. We have to find the P hat first. The P hat will be the proportion, okay, of students that missed at least one class last week out of the 625. All right, and the proportion of that is going to be 139.625. All right, and then 1 minus P hat, we're going to need that as well for checking, is going to be 625 minus 139, right? The remainder of the students that is not part of that proportion, right? Divided by 625. So that should give you 586 over 625, right? So NP is going to be 625 multiplied by this. The 625 cancels out. You get 139. So the test is to make sure that this NP hat product, in this case 139, exceeds 10, right? So that's good. And the same thing here, n times 1 minus p hat. We've got to make sure. So this basically tests the sample size, right? It makes sure that the sample size is large enough because that's when you're going to use the normal approximation to the binomial, right? So n times 1 minus p hat is going to be, of course, the 625 times 586 over 625. So the 625 cancels out. We get 586, which is greater than 10 as well, right? So that's good. And also the third thing to check is that 625 has to be less than 10% of the population, right? Basically, the sample size has to be less than 10% of the population, right? So it makes sense. If 625 is 10%, then the population is 6,250. And definitely what this means is that the population should exceed 6,250 people, right? And that makes sense because the population can never be that small, right? So this is good. So all three conditions are satisfied, this one, and that one. So that means we can go right ahead, formulate our null hypothesis. In this case, notice that your population proportion should always equal to something when you're talking about null hypothesis, because that's the hypothesis that you intend to reject, right? That's your goal, to reject it. Either you reject it or you fail to reject it. That's why the proportion is equal to a certain number. But now the alternative, the one that you're trying to really push down, right, is the fact that the real population proportion of students that missed at least one class is greater than 0.20. Right? So you're arguing with your alternative hypothesis that the real proportion is going to be greater than 0.20, right? Because that's what's being told here. Greater than, right? So this is exactly what you see here as the alternative hypothesis. Okay, so now we have to understand that the alpha level is 0.05. Okay, that's good. And we're going to need a few things. We're also going to need a standard error. And this is going to be found by taking the proportion, the p hat, times the 1 minus p hat divided by the n value. Right? So p hat times 1 minus p hat and divide that by the n value. Right? So if we substitute this in, we should get something like this, 139 times 586. And notice that you're going to have n value 3 times, right? Because each p hat is divided by 625, and so is the 1 minus p hat, also divided by 625. Right, so you're talking about 625 being raised to the cubic power. All right, and 625 to the cubic power like that. Okay, so now let's figure out the rejection z-value, because that's what we're going to need. We're going to need to see the rejection z-value to then compare the observed z-value against. Right, so the rejection z-value is going to be z is greater than or equal to 1.645. Now, how do I know that? We have to verify this result using the normal table. I'm going to show you how to think of that. So alpha level of 0.05 is the 95th percentile in the normal distribution table. As you can see, the 95th percentile will deal with the positive z's, because as you can see, these are the probability values. These are the z-values on the side, the first column and the top row. These are the z-values. But these are the probabilities, okay, respective percentiles that you can think of. So how did I find 1.645? So first of all, I found the 95th percentile. Notice that it's going to be precisely the average of these two, because these two are equally away from 0.95, right? 0.9495 is 5 ten-thousandths away from 0.95, and this one is also 5 ten-thousandths away, right? 0.9505, right? So if you get the average of this, that means you're looking at not only 1.6 for the z, but also you're going to have to average the top values, right? Because that's what they're fighting about, right? These two are fighting for 0.04 and 0.05. Right, so you're going to take 0.04 plus 0.05, you're going to find the average by dividing by 2. So what you're getting is 0.09 divided by 2. This should be added. So you should get 1.6 plus 0.045. That would be easy, so you just get 1.645, right? So that's the z for alpha level of 0.05. That's the z-value that we respectively found at the 95th percentile, right? So that's exactly how I got that value. So notice the rejection starts at 1.645 and goes over it. So if you get a z-value that is 1.645 between these two and above, right, exceeds like 1.7, 1.8, all of these probabilities basically, if you get a z-value over 1.645 for any of these rows, you will reject the null hypothesis and conclude that the alternative hypothesis is true for the population. All right? So let's see the observed z-value and see where we are. Observed z-value. Observed z-value can be found by taking the p hat, subtracting the p, of course, the population probability based on the null hypothesis, and divide that by the standard deviation, of course, of the set of sample proportions. Right? Standard deviation of the set of sample proportions. Okay, so p hat is the sampler proportion minus the alleged population proportion divided by standard deviations of the set of sample proportion, right? So if we do this correctly, you should get 139 over 625 minus 0.2 and divide that by this huge guy. 139 times 586, keeping in mind that all of this is going to be inside the square root, all right? So if you get this, you should get something like this, 1.22, 634, 266. And we're going to round it to the nearest, of course, hundredth, because that's what we're going to use the normal distribution table for, right? Because that's what we have in the z table, the z values, right? Only 2 decimal places. Check this out, right? 1 decimal place, but this is the 2nd decimal place right there, right? So no more than 2 decimal places when you're rounding, when you're going to use the z table. So check this out. 1.23 is definitely less than 1.645, right? Because the rejection z value is when the z is 1.645 and above. But this one that we got, the observed z, is less than 1.645. So that means we failed to reject, right? We failed to reject, right? So fail to reject the null hypothesis. And what does that mean? That means, thus, the claim, and what is that claim? That the proportion of students that missed at least one class is greater than 0.2 is unsubstantiated, right? Basically not enough evidence at the 5% significance level. All right. So basically, there's no sufficient evidence to reject the null hypothesis at the 5% significance level. And 5% significance level is precisely the meaning of the alpha level of 0.05. That's what 5% significance level means. Now, some students are curious to find the p-value, the corresponding p-value that we receive from the fact of being in the observed z region, right? Because we're at the 1.23 region. So to find that, notice that the p-value. So if we look at 1.23, looking at the normal table here, 1.23 is going to give us this probability value precisely. But the thing is, we're interested because that's where we wound up, right? So 1.23 is where we wound up. Okay? And the probability that we're going to find now is going to be anything except this, right? So it's going to be the remaining probability to the right of this value, right? So we're not interested at the 0.8907. And notice that this is a one-tail test, right? So we're looking only at the right end, right? We're not looking at a two-tail test here because there's a greater than sign. So we're going ahead, we're going to the right side. So we're interested in the remainder of the probability in the table here, and that's going to be the probability, right? The cumulative remainder probability. So we have to subtract. Notice that the entire probability table leads to 1. That's going to be the ending of it. So if we subtract this probability value that you see here, 0.8907 from 1, we will get the remaining probability here. And that's exactly the p-value that we must find. That's the probability that will correspond to starting from 1.23 and on and on. All right? So let's do that. So it works the same way like the alpha does. As you can see, alpha is the remaining probability after you hit the rejection region, right? So when you start the z from 1.645 and on to the right side, you will deal with 0.05 and you get less and less and less, right, as you approach the end of the table. So in the same way, just like the alpha, we have to find something that is just like the alpha, but instead of 1.645 and further, it starts from 1.23 and further, right? That's why we have to subtract this value from 1 to get the remaining probability, just like the alpha level was 0.05, right? So that's going to be what? That's going to be 1 minus the probability of z being less than or equal to 1.23, right? Because we don't need anything on the left of this. We don't need this entire value of 0.8907. That's why we're going to subtract it from 1, right? So it's going to be 1 minus 0.89. What was that? That was 07, right? 8907. And that should give us 0.1093. And notice that you can directly compare this value to the alpha level. So the rule is this. The rule is this. When this value exceeds the alpha, obviously you're going to fail to reject the null hypothesis. But when this value is going to be less than the alpha, obviously you're going to be rejecting the null hypothesis, right? Because this will be extremely unlikely to land. But in this case, it's not extremely unlikely region because this is way greater than the alpha. It's twice as much as the alpha level, right? 0.1093. So definitely greater than the alpha of 0.05. So the p-value is basically the probability that, given that, let's say we assume the null hypothesis to be true, what is the probability of getting this observed z-value, right? How likely is it to get it? To get it and go even further or more extreme. As you can see, you start at 1.23 and the further you go, it's going to be precisely 0.1093, and that's going to be the probability. So if it exceeds, this probably exceeds the alpha level, obviously you fail to reject the null hypothesis, right? So in this case, we fail to reject, so we can just write it, failure to reject the null hypothesis, for the reasons being that we already provided. Thank you so much for watching. See you in the next video.